So we've drawn our mirror image. We placed all of our hydrogens in the back. So we flipped this molecule. We placed all our hydrogens in the back. Now what we do is we assign priority. Oxygen is higher priority. The carbon with the oxygen attached is higher priority than a carbon with a carbon attached. Tracing a line from highest to lowest priority, we're moving clockwise, so that's an R stereocenter. Okay, let's look at this next stereocenter down here. So at stereocenter 2, the oxygen is highest priority, followed by the carbon attached to oxygen, followed by the carbon that's just attached to a carbon atom. So tracing from highest to lowest priority, what assignment do we have now? So in blue, from highest to lowest priority, are we moving clockwise or counterclockwise? Is that R or S? S. Okay, now in the last case, we have a pretty interesting motif known as an endoperoxide. Pretty famous motif in the structure of a pretty common pharmaceutical agent, I always mess up the pronunciation, artemisinin. Anyway, it's known for its pretty unique endoperoxide. This is not artemisinin, but it has an endoperoxide. That's why I brought it up. So in terms of priority now, so oxygen, we have a tie. We have a tie, right? This carbon is lowest priority. And now if we go one carbon out, what wins? An oxygen atom or a carbon atom? What wins in priority? Oxygen or carbon? Oxygen. So this bottom endoperoxide is higher priority than our ether. Tracing from highest to lowest priority. Oh. This should be flipped. One moment. Let's redraw this. I realized that when I drew the mirror image, I didn't flip everything. The endoperoxide needed to be on top. That's why it looked odd to me. There we go. Perfect. Okay, so everything's flipped. Our priority assignments still stay the same. The endoperoxide's higher priority. The ether is lower priority. This other group is the lowest priority. Tracing from highest to lowest priority, we get an S stereocenter. So one thing you always have to check is that when you flip your molecule, make sure you flip every motif in your molecule. Okay, so we have the following assignments, S, S, and R, for each of our 3 stereocenters respectively. Does that make sense to everyone? The common mistake I saw in the exam was just assigning priority. Any questions on this first example where we rotated our molecule, we placed our hydrogens in the back, we numbered our groups in order of priority, and then we assigned each center as R versus S? Now, if you want to draw an enantiomer, all you do is you draw the same skeleton, except you flip every stereocenter. So you replace every dash with a wedge and every wedge with a dash. And that gives us the following structure shown here. Does that make sense to everyone? Does that idea make sense? Perfect. So in terms of total stereoisomers, we have 3 stereocenters. So then our total stereoisomers are 2 to the n, where n is the number of stereocenters. That gives us 2 to the 3rd, which gives us 8 for the total stereoisomers. For the other diastereomers, it's solved using 2n minus 2, where you take 2 to the 3rd minus 2, and that gives us 6. Does that calculation make sense to everyone? Does that calculation make sense? Okay, so let's keep going now and let's try to compare whether the following molecules are identical enantiomers or diastereomers. And the way that I do this is by assigning the stereochemistry at each of my centers. One thing that I'd like you to note, is this center with a wedge actually a stereocenter? Is this boxed center a genuine stereocenter? No, no, because remember it has two of the same substituents, has two methyl groups. So then we only have one stereocenter in our molecule, and if we assign the configuration, we notice that this configuration at both of these stereocenters is S. Also, if we rotate our bonds, we find that both of these molecules have the exact same stereochemistry and exact same configuration at all of our stereocenters and the exact same connectivity. So these two molecules are identical. Does that make sense for this first pair? Does that make sense for the first pair? Can I get some yes or no? Perfect. Okay. So for the second set, for these Newman projections, we're going to use the horizontal line trick. So remember, you find a set of parallel bonds and you draw them as part of your main skeleton. So we drew our zigzag pattern. There's our fluorine. There's our methyl group. We draw them in the plane of the page. Everything on the right-hand side of this invisible line gets a wedge. This is the wedge region. Everything on the left gets a dash. Okay, so as we see, we have both the hydrogens with a wedge and the bromine and the hydroxy group with a dash. I've gone through separately and assigned the configuration as R and S respectively, but we actually don't need that entirely. We don't necessarily need to go to that resort just yet. So what we're going to do is I'm going to take this Newman projection and I'm going to rotate it so that my base skeleton is the same. I have my methyl and my fluorine as part of the main skeleton. And as we notice this time, the bromine and hydrogen have a wedge, while the hydrogen and the hydroxy group have a dash. So comparing these two structures, we notice that the only difference occurs at the stereocenter with the bromine. And since we only have a different configuration at one of our stereocenters, what does that tell us? If we have the difference in configuration at one, but not all, we would call them diastereoisomers or diastereomers. Does that make sense to everyone? Does that idea make sense? Perfect. So for the third case in blue, this one you don't even have to resort to assignment. If we look at the dash wedge setup, we notice that at one of our stereocenters, this fluorine stereocenter, we have a wedge instead of a dash. And because we only have a different configuration at one or more, but not all of our stereocenters, we would call these two compounds stereoisomers. Does that make sense to everyone? Does that idea make sense? Does everyone see how the stereochemical configuration, the stereochemistry at the fluorine center is different? Perfect. So let's look at these cyclohexane examples. So looking at this alcohol, is it pointing up or down? Is it pointing up or down? It's pointing up. Okay. What about this alcohol? What about the second alcohol? Is it pointing up or down? Pointing down. Perfect. Okay, now let's do the other one. Looking at this alcohol, is it pointing up or down? This one right here. It's pointing up. Okay. What about the second alcohol? This one right here. Is it pointing up or down? Down. Lo and behold, do our drawings look identical? Are these structures identical? Are these molecules identical? Yes. Perfect. Exactly right. Wonderful. Any questions so far? Any questions so far? Okay, so let's look at this next example for question 3, where we're asked to, for each molecule, draw the 2 chair conformations and then draw the Newman projection for each chair conformation, citing along the C2, C3 and C5, C6 bonds. Okay, so it's really important that your chair conformations accurately reflect the stereochemistry of your structure. So looking at this methyl group, is this methyl group pointing up or down? Down. Okay, so we're going to draw our methyl group equatorial pointing down. Looking at this isopropyl group, is it pointing up or down? Down. Okay, so we're going to draw it equatorial pointing down. Finally, is this methyl group with a wedge pointing up or down? What about the methyl group with a wedge? Wedge tells us what? Pointing up or down? Up. Exactly. So we draw it axial up. Now, if we're sighting down the C3, C2, and C5, C6 bond, we're sighting like so. And so this isopropyl group will be on our right, and the methyl group will be on our left. The methyl is pointing up, the isopropyl group is pointing down. One thing that I do want you to note, how is this methyl pointing, up or down? Looking at this methyl. Where is this methyl pointing? Down, right? So then in the Newman projection, does everyone see how that methyl is also pointing down? Does everyone see how that methyl is pointing down?
Yep.
Perfect. Okay, so in terms of interactions while we're here, we don't have any torsional interactions. We don't have any adjacent substituents, but we do have some diaxial interactions. We have 2 methyl hydrogen 1,3 diaxial interactions that are about 3.8 kilojoules apiece for a total of 7.6 kilojoules per mole. Does this first part make sense? Does this set of drawings and our calculation make sense? And if there's any part that I can explain further, really don't be shy to let me know.
Makes sense to me.
Okay, perfect, perfect. So, continuing on, let's draw the ring flipped product. So, the way that I like to think of the ring flip product, anything that's pointing up will still be up. Anything that's pointing down will still be down. So at position 1, the methyl is down, except this time it is, instead of equatorial, this methyl is going to be, instead of equatorial, the methyl is going to be
Down.
Down, and what do we call that?
Axial.
Axial, exactly right, exactly right. Okay, perfect. Likewise, this isopropyl group, rather than being equatorial pointing down, it is now, is this isopropyl group axial or equatorial? After the ring flip. If it started,
Axial.
it'll end up axial pointing down. Perfect. And likewise, the methyl group, which was originally axial pointing up, is now equatorial pointing up. Okay, When sighting down our bonds, after the ring flip, our isopropyl group is still on our right, the methyl is still on our left, and now let's pay attention to our 1,3 diaxial interactions. So I notice a methyl hydrogen interaction, right? Because both the methyl and hydrogen are axial. I notice an isopropyl hydrogen, and I notice an isopropyl methyl interaction. So adding it up, the isopropyl methyl is roughly 10 kilojoules, the isopropyl hydrogen is roughly 4, and the methyl hydrogen is roughly 3.8. Adding these together, we get roughly 18 kilojoules per mole of strain. So from this, if we compare 7.6 to 18, which of these two chair conformations is lowest in energy for this first structure? The first conformation or the second conformation?
At the top.
Yep, the first one, exactly right. That's why we circled it. It's the lowest energy chair conformation for this first structure. Does that make sense so far? Does that make sense to everyone so far?
Yep.
Perfect. So in the second structure, the only thing that's changed is this isopropyl group. So the isopropyl group, rather than being equatorial, is now axial. So it's pointing up in the axial position. Now, this may not seem like a big deal, but if we look at our 1,3 interactions, now the only thing that's changed between these two structures is the fact that our isopropyl is now pointing up. We've introduced an additional set of 1,3 interactions. So we have a methyl hydrogen, an isopropyl methyl, and an isopropyl hydrogen, and these add up to about 18 kilojoules of strain. Does that make sense to everyone? Does everyone see how changing the stereochemistry of the isopropyl puts the isopropyl pointing up and introduces additional 1,3 interactions? Does everyone see that? Does that make sense to everyone?
Yes.
Perfect. So after a ring flip, all of our axial substituents become equatorial. All of our equatorial substituents become axial. So now we end up with an equatorial isopropyl, an equatorial methyl, and an axial methyl. So in turn, when we look at our 1,3 interactions, we have two 1,3 interactions costing a total of 7.6 kilojoules per mole. So which of these two chair conformations for the second structure is lowest in energy? The top one or the bottom one? Which one is lower in energy? The top conformation or the bottom conformation?
The bottom.
Bottom one, exactly right. 7.6 is less than 18. Now, if we compare these two structures and these two chair conformations, would we expect their energies to be the same or different? Looking at our calculated values, are they the same or different?
The same.
They're the same. That's because these two compounds, if you're paying really close attention, they're identical. They're identical via rotation. Does everyone see that? How if you flip the structure 180 degrees, they're the same?
Yep.
Yep. So if you're stuck on the energy calculations, you can actually backdoor this entire problem if you recognize that these two compounds are identical. So by definition, they must have the same energy. But a large amount of points are allocated to each of these calculations and sort of selecting the lowest energy chair conformation from each pair, as that's a really critical skill, because we're going to eventually build towards looking at different cyclic structures and using the chair conformations to predict the regioselectivity for E2 eliminations. That's why we teach this, partially, in addition to other considerations. Does this example make sense to everyone? Does this example make sense? Any questions on this example?
No.
Perfect. Any questions that gave people a little bit of trouble? Have we gotten to the troublesome questions yet? When I looked at the exams, the questions went pretty well overall. There are just some points that I need to emphasize. So for question 4, I had you draw the structure of 2,3-dimethylbutane and then draw the Newman projections for each of the conformations of 2-methylpentane, looking down the C2-C3 bond. Now, this is a mistake that I commonly see students make. If you look down the C2-C3 bond, let me just put a box around it. What group is hanging off the back carbon? What group is hanging off the back carbon? Is that an ethyl or
Ethyl.
It's an ethyl group. I just saw so many propyl groups, and just remember that when you look down a bond, that there are 2 carbons in that carbon-carbon bond that you're looking down. Just one thing to note. It doesn't actually impact the analysis too much, ironically enough, but it's important to consider. Okay, so we're going to draw all of our conformations. So first we're going to draw the eclipsed conformation where we have our bulkiest substituents lined up. So we have our methyl and ethyl lined up, and we have a methyl and hydrogen lined up. So the methyl ethyl eclipsing is about 11 kilojoules, the methyl hydrogen is about 6, and the hydrogen is about 4, giving us a total of 21 kilojoules of torsional strain. We rotate our back carbon, our carbon-carbon bond 60 degrees, and that gives us the following structure with 2 ethyl. This would be 2 ethyl-methyl gauche interactions, right? Does everyone see the 2 ethyl-methyl interactions? 1 and 2. Does everyone see those interactions? How the ethyl groups and the methyl groups are separated by 60 degrees. And each of those costs about 3.8 kilojoules. One more 60-degree rotation. We have our methyl and ethyl lined up, our hydrogen and methyl lined up and eclipsed, and our hydrogen and hydrogen lined up and eclipsed. And as a result, that gives us about 21 kilojoules of strain. It's exactly identical to the 0-degree structure. Finally, we have our anti arrangement where our bulky substituents are 180 degrees apart and we only have a single methyl-ethyl gauche interaction, which costs us about 4 kilojoules of strain. Is everyone following me so far? Is everyone following me so far?
I am.
Perfect. If you have a question, don't be shy to ask. So another 60 degrees and we have an eclipsed conformation, but it's not as destabilizing because we haven't lined up our bulkiest substituents. We have a bunch of methyl hydrogen eclipsing and ethyl hydrogen eclipsing interactions, which costs us about 6 to 7 kilojoules each for a total of 19 kilojoules. Finally, one more rotation in our 300-degree structure. Again, we have our ethyl and methyl 180 degrees apart, anti to one another. And as a result, this is another low energy conformation because we only have one methyl-ethyl gauche interaction. So we actually have 2 identical structures that are the lowest in energy, the 180 and 300 degree structure. And we have 2 structures that are the highest in energy, which are the 0-degree and 120-degree structure. This is reflected in our graph by the fact we have 2 high points in our graph and 2 low points. Does this example make sense to everyone? Another case where we're calculating steric and torsional strain. Any questions on this example?
Not for me.
Okay. So looking at the following structure, we're asked to indicate the stereochemistry at each chiral center. And it's weird because the first Fisher projection was no problem, but the second Fisher projection gave students a little bit of trouble. That was a little bit strange to me. Anyway, so looking at this, so in Fisher projection, all of our horizontal lines point towards us, all of our vertical lines point away from us. Now what we're going to do is so this should be a hydrogen. What we're going to do is we're just going to turn this structure 90 degrees. And as we notice, we have some substituents pointing up, some substituents pointing down. Now, what we're going to do is we're going to very carefully rotate each of our bonds to put the lowest priority group in the back, the lowest priority group being our methyl groups. Once we've done that, once we've rotated our molecules to put the lowest priority groups in the back, we're now ready to assign priority. So let's draw that just so that way we can work through this process. Okay, so assigning priority, first and foremost at the bottom carbon in red, the alcohol is the highest priority. This side chain that has an alcohol and an aldehyde is higher priority. So we'll put that as 2. And the side chain with the alcohol is priority 3. So then tracing, we move counterclockwise. So this first center is S. The second center, the alcohol is the highest priority, followed by the aldehyde, followed by the side chain with only an alcohol. So tracing, that gives us an R stereocenter. Does this part make sense? This is the part where I often see students made a mistake. Remember, we're comparing a carbon with 2 oxygens versus a carbon with a single oxygen attached. And what wins out? What wins out? So we have a tie for the first set of oxygens, but we have a second oxygen that's not tied with anything. So the carbon with 2 oxygens, the aldehyde, wins out in terms of priority. Does that make sense to everyone? Does that idea make sense?
Yeah.
Perfect. That was a common thing where students arrange the structure in the right way, but they misassigned the priority, and that's why their structure didn't have the right stereochemical assignment. Okay, let's keep going now. This time we have to convert a chair conformation into dash wedge notation. So let's do just that. Oops. So drawing out our basic chair, is this sulfur pointing up or down? Up, so we put a wedge. Is this chloride pointing up or down?
Up. Or well, yeah.
Yeah, pointing up, so we put a wedge. Is the alcohol pointing up or down?
Equatorial down.
Yep, so we give it a dash, okay. So assigning priority, the sulfur is highest priority, the oxygen second, this group is third. So tracing, the first center is R. For our second center, the chloride beats out sulfur. So this alkyl chloride's priority 1, followed by the alkyl thiol, followed by the alcohol containing side chain. Does everyone see that chloride beats out sulfur? Does everyone get that part?
Yeah.
Okay, so tracing from highest to lowest priority, that gives us an S stereocenter. Now, if we quickly reflect and invert, so we're just going to flip this molecule 180 degrees, like a pancake almost. Okay, perfect. Now assigning priority, The alcohol is priority 1. The alkyl chloride's priority 2. Wait, is it? Is it? 1, 2. Yes, it is. And the alkyl group attached to our oxygens, priority 3. Tracing from highest to lowest priority, that gives us an R stereocenter. Does that make sense to everyone? Does that make sense? Make sure to count 1 carbon at a time. Any questions on this example? This is one where I saw a fair number of misassigned centers, but some of them were correct. So that's good to see. Any questions? Any questions on this example? Really don't be shy to ask. If there's anything you want me to go over again in more detail, I'd be happy to do so. Okay, so let's keep going now. In this case, we are dealing with a Newman projection. So again, we are going to use we're again going to use the horizontal line rule, but first we're going to rotate this structure. So we have the following Newman projection. So that way the hydrogen's in the back. Don't worry, we're pretty clever about how we set things up. So the lowest priority groups are always in the back. It's always important to be deliberate when you're taking these steps. Okay, now we draw our horizontal line. That gives us the following skeletal arrangement. Everything on the right side of our line gets a wedge. Everything on the left gets a dash. There should be a methyl group. There we go. So the alkyl bromide gets a wedge. The methyl group gets a dash. Now assigning priority at this first center here. Bromine beats out oxygen. So this alkyl bromide's priority 1. 2 oxygens beat 1 oxygen. So this aldehyde's priority 2. And this other side chain's priority 3. So tracing from highest to lowest priority, that gives us an S stereochemistry. Does that make sense to everyone? Does that process make sense?
Yes.
Perfect. Let's look at the second stereocenter now. So in this case, the alcohol is the highest priority because oxygen beats carbon. The side chain with the alkyl bromides the second priority, and this alkyl chain's the third. Tracing from highest to lowest priority, that gives us a second S stereocenter. Does that make sense to everyone? Any questions on this example?
Nope.
Okay, so let's keep going then. In this case, we're asked to draw the lowest and highest energy conformations for the following molecule. That keyword's really important because one common thing that I saw students do is they would just put all the groups equatorial or axial without necessarily looking at the structure of the molecule. So notice in this molecule, is this isopropyl group pointing up or down? How's this isopropyl group pointing? It's pointing up, right?
Yeah.
Okay.
Axial up.
and this group is pointing down, the ethyl group's pointing down, and the methyl group's pointing up, right? So there's no way, even if I wanted to, for me to draw something that looked like this, for example, right? There's no way for me to draw all of these groups axial up, right? Because the stereochemistry in my molecule does not have them all pointing up. Is that correct?
Mm-hmm.
Perfect. So that's a really important point. You have to always respect the stereochemistry of the molecule that you're given, unless the stereochemistry is unspecified, but since I specified it, you have to follow that stereochemistry. So then, in my highest energy conformation, I'm going to put my two bulkiest groups axial. So what are the bulkiest groups that I can put axial? What's bulkier, the isopropyl and the methyl, or the ethyl group? Which one wins out, the isopropyl and the methyl, or the ethyl group? Which one wins?
First.
Yep, the isopropyl group's way more bulky. So this first structure with the isopropyl and methyl axial is the highest in energy, while the structure with the ethyl group axial is the lowest in energy. Does that make sense to everyone? Does that idea make sense?
Yeah.
So the highest energy chair conformation has the most substituents in the axial position. Okay. Likewise, for the lowest and highest energy conformation of the following molecule, the highest energy conformation will be the eclipsed conformation, where our bulkiest groups have 0 dihedral angle. So in this case, we have a T-butyl group and we have an ethyl group. So we're going to place the T-butyl group and the ethyl group smack dab eclipse with each other. So that gives us our highest energy conformation, while our lowest energy conformation has the greatest separation between our bulky groups. So we place our T-butyl and ethyl group 180 degrees apart. We call this the anti-conformation, as we talked about in class. Does this example make sense? Does this example make sense to everyone? Now, just to make sure you're paying attention, here, what is a problem with this structure? Why would I not give full points for this structure as the lowest? So if we look at the correct response, we have just a T-butyl methyl gauche interaction. What do the interactions look like in this proposed structure? What do the interactions look like?
T-butyl methyl gauche, and then the
Yep.
ethyl methyl gauche.
Yep, exactly right. Does
But
everyone notice?
Isn't that the same thing on the other one though?
So,
wait, hold on. Oh, sorry, never mind. I'm just looking at an inverted version of it.
Not quite inverted. They're just, it's just via rotation. Let me rephrase. Since the stereochemistry is not unspecified, we're comparing and we're trying to draw the lowest energy possible conformation for this structure. And if we compare, placing the methyl group on the opposite side generates a greater number of steric interactions compared to the methyl group on the opposite side. And since the stereochemistry is left ambiguous, we can consider both of the possible stereoisomers. Does this example make sense to everyone? Does this example make sense?
Yeah. What I did for mine, which I think I'd see the error in it, was I had the T-butyl and the ethyl in gauche position, and then the two methyls gauged. I was just curious because I wasn't sure. Yeah, because my theory behind it was if you have the T-butyl and the ethyl, yes, it has a high like strain, but at the same time, the two methyls would have a lower, like I thought that it would have a lower strain than like a methyl ethyl and a T-butyl methyl.
Yeah, looking via rotation, if we were looking at that system, we could rotate it and get something like this. And that way we have a hydrogen that's sandwiched rather than a methyl group. And that would be a little bit lower in energy. So you're very close. It just requires one more rotation.
Gotcha.
Essentially, you want to avoid sandwiching your bulky groups. So you want to, if you have two bulky groups separated in the front, you want to place the least bulky group in between them in general.
Oh, okay, yeah, because the way I had mine was the T-butyl was at the top, the methyl was at the bottom right, and then the hydrogen at the bottom left, and then I had it, you know,
let's entertain that possibility.
Yeah, just because I'm just trying to understand, because I understand, but I was just trying to see if my thought process was opposite.
Like this?
Wait. Yeah, so here, look, I can annotate. That's right. So I had it like this. The T-butyl. And that's a methyl over here too.
Oh, okay. So hydrogen methyl.
Yeah, because my thought process was like, because these two are gauche, but that would be a lower gauche because it would be just a 3.8.
Yeah, that's the second best. That's the second best possible solution.
Oh, okay. But this one is just preferred because it just has, so the methyl T-butyl and the ethyl methyl is still a lower strain than this one.
Yeah. So
Okay.
this one has an ethyl T-butyl and a methyl. And because the T-butyl is so bulky, it's more sensitive to this more bulky ethyl group.
Oh, okay, I see. Because like okay, I gotcha.
Yeah. So in terms of, and that's a really good point to bring up, because there is this ethyl methyl gauche interaction. So if you look at these two structures, if we fully analyze them, are both equally acceptable. The only difference is you have to keep your ethyl group away from the T-butyl group. It's good that we pointed that out. And that's mainly what I was looking for. If you did that, I took off like a point, but you still got the majority of points for the question.
Yeah, you did. I was just curious. I just wanted to see if like my logic made sense, but
it's pretty close. But essentially, if you have a really bulky group, you want to get the bulky groups away from that other bulky group.
Well, yeah, now that I think back to it, like I can imagine, because like the two bulky groups, just there's more room for them to interact, and so yeah, I get it now. That's just this one would be the best possible answer. So I gotcha. Thank you.
Mm-hmm. But it's good to see that answer was proposed. It's good to see that there are sort of multiple like sort of gradations in terms of the different answers, and it's good for us to discuss that, because I personally don't like to score all or nothing, but I always like to consider what's the student's logic, and when I see that they've calculated the energy values and their argument is consistent, then I can give them more points. And
yeah, and you did. Thank you.
Pretty close. But that's a really good question to ask. So thank you for bringing that up. It's great to have because we're going to be analyzing Newman projections when we talk about elimination and substitution reactions. So they aren't going away, actually.
Ew. Okay.
Don't worry, it's not as bad as it sounds at all. Okay, so these ones, these two questions are probably the biggest loss of points that I've seen so far on the exam, and it's one thing that I always want us to pay attention to. What do we notice when we have a dash and a wedge? What does that tell us? What should we consider?
Trans,
yes, and stereochemistry, right?
Mhm.
So then, because these are stereocenters, the stereochemistry has to be included in the name. Remember how we talked about if the stereocenters are real stereocenters, you have to specify the R and S configuration? That is crucial in this problem. You can also call this trans, that indicates the relative stereochemistry. That's acceptable. It's not 100% correct, but I gave credit for it because it's technically a reasonable name. So most students got the 1-ethyl 3-methyl cyclohexane correct. But remember to assign the stereochemistry, both of these centers are R, and you put 1R, 3R, 1-ethyl 3-methyl cyclohexane. Does that make sense to everyone? When you have stereocenters, the stereocenters have to be included in the name. Does that make sense?
Yeah, got it.
Perfect. Same for this one. This one, it's a little harder to see. So let's convert this into a dash wedge structure. So is this ethyl group pointing up or down? Up, yep. Is this isopropyl group pointing up or down?
It's down.
Down, exactly right. Okay, so then assigning our centers, looking at this first center. So we have priority 1, 2, and 3, tracing. Oops. Whoops, that's not right. Priority 1, 2, and 3. To showcase that, priority 1, so tracing out. So tracing out, we have an even tie. Tracing out once more, we have 3 carbons attached, so that wins out as priority 1. Tracing out one more, we notice that a carbon beats a hydrogen. So that's why this is priority 2. So tracing, that gives us an S stereocenter. Oh, oops, wrong way. I keep getting that mixed up. There we go. So tracing from priority 1 to priority 3, that gives us an R stereocenter. Does that make sense?
Yeah.
Perfect. Now for the other stereocenter, we flip our molecule, and that gives us the following. So ranking, the isopropyl group is priority 1, the side chain closest to the ethyl is priority 2, and just the normal alkyl chains priority 3. We get a clockwise rotation from highest to lowest priority, and that gives us an R stereocenter. So this would be 1R, 3R, 1-ethyl 3-isopropyl cyclohexane. Again, the stereochemistry has to be labeled in the name. It's a big deal. You're going to see questions like this on the ACS. So that's why I want you to be able to process these. Does that make sense to everyone?
Yep.
Perfect. Perfect. Okay, the extra credit question. Just as a side note, does anyone know where this extra credit question came from?
I don't, but it drove me crazy. So that's all I know.
Does anyone have an idea where it came from? Does this question look familiar? I guess is what I'm trying to imply. Have we seen this question before?
Was it in the homework?
Yes, it was.
Of course.
Yep, it was in the chapter for homework. Yep.
Of course.
Actually copied almost word for word, except without the methyls instead of an ethyl. Okay, so the gimmick for this question is that a hydrogen bond is about 20 kilojoules. So it overwhelmingly beats out any penalty from Gauss interactions. So then, essentially, the majority of points were given is if you have a set of, essentially the majority of points were given if you have your two alcohols positioned so that they're Gauss to each other and that they can hydrogen bond. So the anti-structure is actually higher in energy than the Gauss. That's why this example is so cool. You can also see this if you have a carboxylic acid, same principle. Okay, so there are a few permutations of possible answers. There are a few permutations of possible answers. And although these two structures look very close to each other, one of these structures is in fact lower in energy. In this top example, the one in the box, we have an oxygen methyl, or sorry, we have a hydroxyl methyl. We have two Gauss interactions and an alcohol Gauss interaction. And a hydroxy group has an A value of roughly half of a methyl group. So we'd estimate this to be around 1.9 times 2, or roughly 4 kilojoules. A hydroxy should be about a fourth, or around 1 kilojoule. So we have 5 kilojoules of strain. So we have a hydroxy Gauss, which is around 1 kilojoule. Because if you look up the A values for a hydroxy group, it's approximately 1/2 the A value of a methyl group. Okay, then we have a methyl-methyl interaction, which is about 4 kilojoules. And we have a methyl hydroxy interaction, which is about 2 kilojoules. And that adds up to 7 kilojoules. So this is the most optimal answer, and this is the second best answer. As long as you drew the alcohol's hydrogen bonding, I gave you the majority of the credit. Does that make sense? A hydrogen bond is 20 kilojoules, so it completely obliterates any energy savings that you get by putting your alcohols anti to each other. Pretty cool, right?
Yeah, now that I look at it.
Don't worry, it was only 4 points of extra credit, not a lot. I always try to include things in the homework that are interesting. I wouldn't call them gimmicks because they do pop up and they are relevant in terms of dictating the stereochemical outcome of reactions. Like the same principle would apply if you have like a carboxylic acid, for example. This question, when I was tutoring for the MCAT a lot as an undergrad and as a grad student and so forth, this is a pretty common MCAT question because it focuses on reasoning, combining the reasoning of Newman projections with considering intermolecular forces. The same thing would work if you had like a carboxylic acid, for example, because that can also hydrogen bond.
So that makes sense.
Mm-hmm. And this is important because if you have these alcohols adjacent, that affects the lowest energy Newman conformation, and that can bias reactivity patterns. It can lock the molecule in certain conformations. Anyway, so the main point I have for this is don't neglect to look over the homework. Yep, I provided the hydroxy Gauss interaction. Yep, but the point of that homework question was to think for a second. Wait a second. Why is it marked off? Why is it not? Why is the anti not the lowest? And sometimes there's always like one or two of the homework questions that are designed to provoke a little bit further thought and reading. And I think this one's also brought up in your book. But if you have any questions about the homework questions, you can certainly bring them to office hours, and I'd be happy to ask. Oh, energy values calculated in Marvin sketch aren't the most accurate. I wouldn't use Marvin Sketch for energy optimization. It's fine for spectra estimation, but energy estimation from computer programs is, how do I say this? In my opinion, it's not very good. It's not very accurate. Otherwise, we'd be using computations for more sophisticated predictions. I guess that's my perspective. Empirically, a lot of these lowest energy conformation, these compounds of these conformations have either been observed or the barrier to rotation has been observed and studied more and using more empirical methods. So that's the exam. It took us an hour, roughly an hour to walk through it. So it's not too bad. I'd say exam 3 is really when we're applying all of these concepts. We'll have exam 3 towards the end of the semester. It's good. It's good that this exam was fun because a lot of these skills are going to be tested again in exam 3. That's good. That's good. It's good that students are comfortable with stereochemistry because, as you noticed in class today, we're going to be assigning a lot of stereoisomers in the next few sessions. So with that said, do we have any questions that I can address? Are there any questions that I can address? So just as a reminder, we have the elimination lab due this week. We're going to be starting another lab next week. And just as like a general comment, don't worry too much about the labs. We still have plenty of labs to go. I've made sure to troubleshoot a lot of the issues with how the feedback is popping up and making sure that any of the submissions, even late, have been fully scored. If there are any reports that you'd like me to go over with you during office hours, don't be shy to bring it to me. Let me just pause this recording.